Alrighty, kiddos, welcome back. We're here for the second half of our review. We just finished up periodic properties, and we're going to talk about bonding in this review. Now, on your own, kiddos, please take some time and review ionic bonding. Now remember, that's where electrons are transferred from a metal to a nonmetal. They're not shared. Also review lattice energy. So both of those could certainly be topics on your exam. So please, on your own, review ionic bonding. I'm going to concentrate this review on covalent bonding. And as such, electrons will be shared. We can illustrate that quite nicely by drawing Lewis structures. So we're going to begin by CH4, and we're going to begin by counting the valence electrons. So let's find carbon on our periodic table, and carbon is in group 14. Its configuration ends with 2s2, 2p2, so it has 4 valence electrons. So we have 4 valence from the carbon. And then there are 4 hydrogen atoms, and let's see, hydrogen's over here in group 1. Its configuration is 1s1. It has 1 valence electron, so 1 valence for each of the 4 hydrogens, and that gives me a total of 8 valence electrons. So we've gotten that taken care of. Let's put carbon in the center here, and then we're going to draw a bond between it and each of the hydrogen atoms. So on all 4 sides, we are going to draw a bond. And we're going to count how many valence I've used: 2, 4, 6, 8, which is exactly what I'm allowed. So that is the Lewis structure for CH4. Now the bond angle. Now remember, this really is not on 2 dimensions. It's a 3-dimensional structure. So if I could try to draw it here, I'd have one of the hydrogens coming out up top, one coming out in this direction, one coming in this direction, and one coming out of this image at you. And so the angle's not 90 degrees. This angle, all of these angles are the same as each other, is 109.5 degrees. So that would be my bond angle. Now the shape of this, since there are 4 electron pairs, or 4 regions of electron density around the central atom, and all 4 are bonding, is tetrahedral. And it is quite symmetrical, so it is non-polar. You can use your spaceship analogy to help you determine that, but when all of these dipoles are added together, they end up canceling, and so we end up with a non-polar molecule. So let's see, we've got the valence electrons, boom, we've got the shape, we've got the bond angle, and we've got the polarity, of course, as well as our Lewis structure for CH4. Okay, let's move on to the next one now. So we'll clear this page, and we will do HCN next. So we already know HCN. We already know the H has 1 valence, and carbon has 4 valence. How many valence does the nitrogen have? Well, nitrogen's in group 15. Its electron configuration ends with 2s2, 2p3, so 2 plus 3 gives me 5 valence for nitrogen. So we end up with 1 plus 4 plus 5. We have 10 valence, and I will be allowed in my Lewis structure. So if I were to draw this, I would put carbon in the middle and hydrogen on one side, nitrogen on the other. I could try one pair between the carbon and the hydrogen and nitrogen, but to do that, I would still need a pair above and below carbon to give it its full octet, and a pair above to the right and below nitrogen to give it its full octet. And in that situation, I'd be using 2, 4, 6, 8, 10, 12, 14 valence, which obviously doesn't work. So we have to have multiple bonds here. So I'm just going to jump right to the chase since this is a review, and I believe we actually did this one in our notes. I'm going to try a triple bond between carbon and nitrogen, and I can only have a single bond between carbon and hydrogen because hydrogen only has one energy level, and that can only hold 2 electrons. I'll put 2 more dots there to finish up nitrogen's octet. So you can see the nitrogen part of this molecule has 8 electrons around it, or 4 pairs, and the carbon part of this molecule has 4 pairs around it. And I've used 2, 4, 6, 8, 10 valence, which is exactly what I'm allowed. So there's my Lewis structure. And you can see around the central atom I have a region of electron density going this way and one going that way. And so they're going to push against each other and be as far away from each other as possible, and hopefully you can see that that bond angle is exactly 180 degrees, and we call that a linear molecule. Now in this situation with a nitrogen over here, which is very electronegative, more so than the hydrogen, we have a dipole going in this direction. And there's not as strong of a dipole pulling in that direction. So the dipoles do not cancel out. And so this molecule would be polar. So it's polar, it's linear, bond angle 180 degrees, and there is your Lewis structure. Okay, let's go on to the next compound here. And so we have BeH2. So BeH2. Beryllium. Beryllium's in group 2. It's right here, folks. Its configuration ends with 2s2, so it has 2 valence electrons. And there are 2 hydrogens, and we've already determined in an earlier problem that they have 1 valence electron. So 2 plus 2, I have 4 valence I'm allowed to deal with. Now recall that beryllium is one of the exceptions to the octet rule. Turns out to be stable with just 2 pairs around it. So if I put it in the middle and put a bond between it and a hydrogen on one side and a hydrogen on the other, I don't need to add any more because this is an exception, beryllium, to the octet rule. And so we have 2 regions of electron density. That's it. And so that angle is again 180 degrees, and we would call that molecule linear. Now in this situation, we have a dipole pulling in this direction towards the hydrogen, and a dipole with the same strength pulling in the other direction. And so these guys cancel themselves out because the dipoles are the same magnitude, and so they add up to 0. So that molecule would be nonpolar. Nonpolar, linear, 180 degrees, and I've given you the Lewis structure. Okay? Now hopefully you folks are taking some time to try these on your own before I do it for you. That's the plan at least. Okay, the next one on your worksheet you will see is Po4. It's an ion, and the overall molecule has a 3 negative charge to it. So let's go ahead and figure out our valence. Let's find phosphorus. Phosphorus is right here. It's in group 15, so we know it has 5 valence. There are 4 oxygens, and oxygen's in group 16, so oxygen's configuration ends with 2s2, 2p4, for a total of 6 valence for each oxygen atom. So 6 valence for each oxygen. Now we have that 3 negative there. Now if you remember, that means I have to add 3 valence to the total. Electrons carry a negative charge, so when the overall molecule is -3, we've added 3 electrons. So we end up with 5 plus 24 plus 3, that's 29, 32 valence electrons. So I've got my valence. Let's put phosphorus in the middle here. And we'll bond an oxygen to each of the 4 sides. And then we'll give oxygen a full octet by putting 3 more pairs around each oxygen atom. Then to finish this off, we'll put brackets around it. Remember, ions, we draw brackets around to let the reader know that it's an ion. And we'll put a 3 negative on the outside to let them know how many electrons, in this case, that we've added. Now, that molecule really doesn't look like that. Remember, we have an oxygen up here, one coming out to the side here, one over here, and one coming out of the paper at you. And remember, these bond angles here are all congruent. They're all the same as each other. And remember, there's 4 regions of electron density, and all are bonding. That angle is 109.5 degrees. Okay? And we call that a tetrahedral shape. Now normally, tetrahedrals, where we have the same atoms bonded to the central atom, normally we'd say they're nonpolar. But since this guy is an ion, we are going to say that it does have an uneven distribution of electrons, so we would call it polar because it's an ion. Okay? Alrighty, next up, O3, right down here. So that's an easy one, O3. We have 3 oxygens, and we just found that oxygen had 6 valence. Remember the last problem? So we have 18 valence that we're allowed to work with here. So we'll put O in the center, right? Sort of a dumb thing to say. We'll put an O on either side. We'll try 1 pair between them, and we'll give this oxygen a full octet by putting 2 more pairs around it. And this oxygen, we're going to add 3 more pairs to give it a full octet, and the same thing with this guy over here. So let's see what we've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Huh, we're only allowed 18, so that ain't going to work, is it? So let's try another one. We'll try a double bond here between oxygen 1 and 2, and we'll put a single bond there. Then won't this oxygen need 3 more pairs around it to complete its octet? This oxygen here just needs 1 more pair to complete its octet, and this one only needs 2 more pair, doesn't it? So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, that's what we need. So that Lewis structure doesn't look too bad, but I'm forgetting something. Is there really just 1 single bond here and 1 double? No, as you recall, we have something called resonance structures. It's really a bond and a half between each of the ozone oxygen atoms. So we'll put another structure with the double bond on the right-hand side, and then we'll complete the octets for each of these before we say that we're finished with the Lewis structure. So this would be the Lewis structure for O3, and it shows resonance. So it's really not a single bond and a double bond. It's really 2 bond and a halves. Now, we have 3 regions of electron density. We have 1 region of electron density here, 1 here, and 1 there around the center atom. So that might look linear, but it's not, kiddos. What we end up having, folks, is an oxygen here, and then we have 1 here, 1 down here, because this non-bonding pair is pushing those down or away. I'll just draw a double bond there so you're not too confused. But that non-bonding there, even though it's not bonding anything, it still influences these bonding pairs here and here, so it bends it down. So we have 3 regions of electron density. When we have 3 regions, we would like to say that this angle here is 120 degrees. But let's not write that down too quickly. Remember, non-bonding pairs, they take up a bit more space than bonding pairs, remember? And they reduce the bond angle by about 2 degrees for every non-bonding pair. So that's really not 120 degrees. It's actually closer to 118 degrees. Okay, and because we have this bent configuration, it's not symmetrical, the ozone molecule is actually slightly polar. It's a slightly polar molecule. So we've got the Lewis structure, polarity, bond angle, and valence electrons. It looks like there's one more to do on your review sheet, and that's SO3. So let's figure out our valence. We have sulfur here. Here's sulfur. It's in group 16. So we already figured out that that has 6 valence. And we did oxygen a couple of times now. Each oxygen has 6 valence. So we have 24 valence that we have to work with here. Put sulfur in the middle. And we'll try a single bond to each of the oxygens. We'll see if that works. Complete this oxygen's octet. Put 2 more there for sulfur's octet. And this oxygen's octet. And this oxygen's octet. Let's see what we have here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We're only allowed 24, so that ain't going to work. So let's try a double bond over here to this oxygen and a single bond here and there. Now that sulfur has a full octet. This oxygen just needs 2 more pairs to complete its octet. This oxygen needs 3 more pairs. And this oxygen needs 3 more pairs. So we use 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yeah, that's it, but we're not quite finished. Is that really 1 double bond and 2 single bonds? No, it is not. It's really 3 bonds and a third. So that double bond is spending time in all 3 positions. So we show that by drawing resonance structures. So we're going to draw the double bond to the left, oxygen, and then we're going to draw one more time to the oxygen on the, not there, we already drew it there, didn't we? So I'll draw it one more time to the oxygen on the bottom. And we'll finish up these octets. So there's my Lewis structure for SO3. And you can see we have 3 regions of electron density around it. So we have draw a double bond there, 1 there, and 1 there. And so when they're as far away from each other as possible, when we have 3 regions of density, these angles will all be congruent. And you remember what that is? That's right, it's 120 degrees. And there are no electron pairs on top to push that down into a 3-dimensional type of image. This is flat, it's planar. So we have a 3-sided planar object. So if you recall, we call that trigonal planar. Okay. And then finally its polarity. Well, it looks like we have a dipole going this way. A dipole, let me see, that's getting a little bit confusing. Let's erase some of this and redraw it, folks. We have those 3 oxygens there. Okay, we have a dipole going this way, and this way. You can use your spaceship analogy and quickly determine they're going to cancel each other out. So this guy here would be non-polar. Okay? Alright, if you can do the ones I've done for you on this review, you should be fine on your exam. I'm not going to put any expanded octets on your test this year, unless it's extra credit. So you guys should be okay with these. Go through the ones in your notes, please. Watch the videos over again, and I think you'll be in good shape. Okay? So good luck on your exam, folks. See you soon. Bye-bye.